BLAST is the short name for the basic local alignment search tool. It's a heuristic approximation to Smith-Waterman algorithm. It examines only part of the search space, and as a result, it sacrifices some sensitivity and cannot guarantee to find optimal alignments. But the gain in the speed is huge, and the heuristic method is used to reduce the search space is to scan the database sequences for likely matches before performing more rigorous alignments, and only perform more rigorous alignments in the area has the likely matches. So the central idea for BLAST is to only consider or confine attention to sequence pairs that contain an initial word pair match. So how BLAST works? There are 4 basic phases. Phase 1, compile a list of query seed words. Usually the seed word is 3 for protein and 11 for nucleotide, and the latest it increased to 6 for proteins and 28 for nucleotide. And for example, the query sequence RGG VKRI, it can generate a list of seed words as RGG, GGV, GVK, and extra every time just shift one position, one amino acid. Phase 2, expand the word pairs to include those similar to query. How to define the similarity? Usually it's defined to above certain threshold. Usually the threshold is 11, and we use the substitution matrix to calculate the match scores. For example, again the same query and the same seed word as last slide. This time we extend those seed words to its neighboring word. RGG, its neighboring word is RAG, RIG, RLG, and extra. And the GVK, its neighboring word is GLK, GIK, and GGK, and extra. We list all the possible combinations, and then we use a similarity threshold to cut it off. For example, GVK and GLK, we can calculate the match score for GLK based on the Blossom 62 substitution matrix. G and G, its score is 6, and from V to L, the score is 1, and from K to K, the score is 5. So the GLK match score is 12, and usually the similarity score cutoff is 11, so we can keep this neighboring word GLK. In phase 3, a database is scanned to find the sequence entrants that match the compiled word list. So for example, here the GLK in the database sequence perfectly matches the GLK in the query sequence. And here, how to scan the database is also very important. The database should have a pre-established index table, so we can not only quickly locate the related candidate sequences in the database, but also locate the matching positions in the candidate sequence. And by properly designing the index structure, this step can be done in linear time. This way, it greatly improves the efficiency. And in phase 4, the initial database hits are extended in both directions using dynamic programming. And the matched word is used as the local alignment seed. Here, the matched word GVK and the GLK is used as the alignment seed. And use dynamic programming, the Smith-Waterman algorithm, to search for high-scoring alignments. And here is the alignment result. The red path corresponding to 6 matches, 1, 2, 3, 4, 5, 6, and 4 mismatches and 1 gap. We have an alignment score based on certain scoring matrix. BLAST returns the highest scoring hits in a ranked list. Now let's look at some details in the BLAST output. The BLAST output is a ranked list of the hits. The first column and the last column is some details about the target sequence, its name and description, its accession ID, and a link to the detailed annotation website. And the middle part is about the alignment statistics. The maximum score is the highest alignment score calculated from scoring matrix or substitution matrix. It's for a certain segment or a certain seed. The total score is the sum of alignment scores of all segments from the same subject sequence. The query coverage is the percent of the query length that is included in the aligned segments. The maximum identity is the highest percent identity for a set of alignment segments to the same subject sequence. The e-value is very important. It's an important feature of BLAST, and it computes the statistical significance for each hit. So because the large data volume, it's very critical to provide some measurements or measurement statistics for the statistical significance of a given hit. And when we're talking about the statistical significance, we will think about p-value, false discovery rate. And here, the e-value in some way is similar to p-value, especially when the e-value is less than 0.1. The number itself actually is very similar to p-value when it's less than 0.1. However, there is a very large difference between e-value and the p-value, that the p-value is a probability number. It has to be less than 1. And the e-value is an expectation number. It can be larger than 1. And when we calculate the e-value, we have considered many other factors that is not considered in the p-value. So again, the e-value is the expected number of hits that are as good or better than the observed local alignment score if the query and the database are random with respect to each other. In another word, the p-value measures how a match is likely to occur by chance, and typically only hits with e-value less than a significant threshold are reported, and this is equivalent to selecting alignments with a score above a certain threshold. And ideally, a threshold separates all query-related sequences from all query-unrelated sequences. It separates the yellow part from the gray part. However, unfortunately, in reality, often the two score distributions overlap. The alignment score of unrelated sequences overlaps with the alignment score of the related sequences. And the e-value provides an estimate of the number of false positive hits, that is in the red area. E-value is calculated using this formula. This formula was derived by mathematician Sam Carlin. M is the length of the query sequence. E-value is proportional to the length of the query sequence. This is because BLAST is a local alignment and does not require a full-length match. N is the size of the database. E-value is also proportional to the size of the database. This is easy to understand. The larger the database, the greater the chance of random matching. E is the natural logarithm. S is alignment score. There is a negative sign before S. E value is negatively correlated with alignment score S. If the alignment score is higher, the chance of random match is lower. K and lambda are related to the scoring matrix and the search space, behaving like a normalization factor to balance the impact of different scoring matrix and the search space on the results. In general, E-value less than 0.005 are usually significant. To find out more about the E-value, you can look at the NCBI BLAST website and this paper in Genobiology. Okay, let's summarize it briefly. BLAST is different from the algorithms based on dynamic programming, such as Needleman Watch, Smith-Waterman. Dynamic programming is an exhaustive strategy. It searches the searching space exhaustively, and so it has good accuracy, but relatively low speed. In contrast, BLAST is a heuristic algorithm. Heuristic in Greek means find or discovery. It's a technique to solve a problem by a practical method that is not guaranteed to be optimal, but is good sufficient. So for example, it's not guaranteed to find a global minimum, but may only end up with a local minimum. So that means BLAST does not guarantee to find an optimal solution, but tries to find a sufficient solution in less time. That's why it has a very great performance in both accuracy and speed. The key heuristics for BLAST is to use the seeding and extending strategy to apply dynamic programming algorithms only in selected areas. This effectively reduces the amount of computation and increase the computation speed. However, the increase in speed comes with a trade-off in sensitivity. So especially for distant species.